All right, welcome back to lecture 2. We are actually going to start getting into some of the more meaty material of the class and talking about and learning more about Antarctica at this point. So we will start off with geography, the wheres and whats, and also whos of Antarctica, because we will talk about the people that live in Antarctica and where they live, but there's not many of them. This first half of the lecture is more closely about the physical geography of Antarctica, talking about some basic divisions between parts of Antarctica, important features, and also an introduction to maps, and a look at some of the features of the biggest continent, why it's so cold, why it's so dry, why it's so high. And as I mentioned, a lot of this is going to relate to maps. Like this picture, a topographic map of Lake Vanda, which is actually where one of my campsites was during my field season. During one of the labs, you will actually make a topographic map yourself, and you will work on topographic maps yourself, and I will talk about them in this lecture. So Antarctica is extreme and it is unique, and I am not particularly fond of either of those words because they get thrown around a lot, but it's hard not to be dramatic when you talk about Antarctica. It is the coldest continent, both in terms of average temperature and also in terms of the fact that it is where the coldest temperature on Earth has ever been recorded. It is also really windy. The wind chill makes the cold much, much worse. And Antarctica, the wind is always blowing, it seems. And that's something that people do realize about Antarctica. Something that people may not always realize is that it is, on average, the driest continent on the planet. Now, the Atacama Desert in Chile has may beat it in terms of being the driest individual location, as in there are some years where there is no precipitation there. But if you take the data for the continent of Antarctica and average it, you get a very low amount of rainfall compared to, say, if you take all of the data from the rainfall on points on the South American continent and get that. South America, where the Atacama Desert is, has that dry part, but it also has the Amazon rainforest. Antarctica is just a big desert all over. It is a cold, windy desert, and it receives very little snowfall. What snowfall is there has just had a very, very long time to accumulate. It is the highest continent, only on average, because Mount Everest is higher, but we'll talk about how the glaciers even out everything and give the impression that Antarctica is kind of just this one big dome. There are lots of mountains in Antarctica. Some of them do poke out, as you can see in this picture I took, but a lot of the features are just covered by ice, and it's also the least populous continent. Nobody lives there permanently, and you have a couple thousand people on the continent at a given time at most. That's fewer people than live in the city of Goleta or who go to UCSB. The coldest temperature ever recorded on Earth was in Antarctica. And when people ask me about how my experiences in Antarctica were, it's really hard for me not to just go, it was cold, because that's kind of the basic answer. But aside from the fact that Antarctica is just cold in general, it reached almost 90 degrees, negative 90 degrees Celsius, or negative 128 Fahrenheit, 129 Fahrenheit, as this retouched Robert Munch classic book here illustrates. And that's not the average temperature. That is the coldest ever temperature recorded at the Russian research station at Lake Vostok, which, as we'll learn, is quite far from the ocean, and that plays a big role as to why it got so cold there. And in general, the fact that Antarctica is a large block of continent, unlike the Arctic, it's not an ocean. Well, if you're taking an average temperature, you're going to be taking data points from the center of the continent too, and a lot of Antarctica is really far from the ocean. The continental effect is the fact that the farther you are from the ocean, the colder it is, or in general, the more extreme temperatures are. But in the poles, it just means the temperatures get more extreme. However, Antarctica is especially cold for a couple of reasons besides this as well. Something we'll talk about a bunch is that the water around Antarctica is isolated from warm ocean currents that could potentially bring more heat to the continent by the Antarctic Circumpolar Current, the current that runs all the way around Antarctica. And something that also applies to the Arctic is that because you are so far from the equator, the sunlight hitting the Earth is more spread out there, and the tilt of the Earth's axis makes it so that even though during the Antarctic summer, the Antarctic is pointed straight at the sun, during the winter, it's pointed straight away, which puts much of the continent into complete darkness and contributes to annual average temperatures being really cold, because no sunlight means it's really cold. And we'll talk more in depth about the role of sunlight and distance from the equator later in this lecture. But this all produces a really cold continent. The average temperature is 60 below 0 degrees Celsius in the interior and 10 degrees 10 degrees Celsius below zero on the coasts. Why is it somewhat milder on the coasts? That is a lot to do with the continental effect that I just talked about. So Antarctica is actually a lot colder than the Arctic. The South Pole is a lot colder than the North Pole. And this is because the Arctic is an ocean. The Arctic, there's no continent called Arctica. There's Greenland and there's surrounding continents, but the Arctic is an ocean. And why is this important? Because an ocean's made of water as opposed to rock. This is important because substances have something called a heat capacity. And the heat capacity is a physical property. It's usually going to be somewhat inherent to a substance like water or a mineral based on its chemical structure. Water has an extremely high heat capacity, and that is 4.18 joules per grams per degree Celsius. And what that means is that you need 4.18 joules, which is the unit of energy, which is one particular unit of energy. You need to pump that much energy into 1 gram of water to raise it by a degree Celsius, because temperature comes from the heat being put into it, from energy. If that doesn't sound like a lot, compare to the heat capacity for granite, the rock that makes up most of Antarctica and also most of California, most of the continents in general. You have 4.18 joules for water and then 0.79 joules for granite. So what does this mean? It is much easier to change the temperature of rock than it is to change the temperature of water. If it's easier to change the temperature of something, that means more wild temperature fluctuations. So the ocean actually regulates temperature very well because it can absorb a lot of heat without changing temperature much, and it can also release a lot of heat without changing temperature much. So that means that generally by the coast, including by the coast of Antarctica, you have milder temperatures. You saw in the last slide that the temperature is much less horrifying on average at the coasts than in the interior, and that's because the ocean is there. The Arctic Ocean water is not going to drop below 2 degrees Celsius. The salt water isn't going to get much colder than that without freezing. And the whole Arctic Ocean isn't going to freeze. So the water, that massive water nearby, is relatively warm, and it helps moderate the surroundings. The interior of Antarctica is really far from the ocean, and that's why the most miserably cold parts of Antarctica are extremely far from the ocean. The Antarctic Circumpolar Current, which we will talk about more in depth, is also really nicely visible in this diagram on the right. The darker colors mean colder water, and you'll notice the Arctic isn't even above Siberia and Alaska, it's not quite as uniformly just a dark band. The water surrounding Antarctica is generally a lot colder, and that is because there is a current running all the way around the entire continent of Antarctica, past South America, past Africa, and past Australia, going extremely fast and also blocking warm water from reaching the Antarctic. The continental effect is actually something that we see in the United States. Us in California have it relatively easy compared to a lot of people because, for one thing, we really don't have seasons. And there's factors involved in that, but a lot of it has to do with the fact that we are by the ocean. Now, the coasts tend to be relatively mild, both the east and west coast, and you might be confused when I describe the east coast as relatively mild, but it doesn't get as cold on the east coast as it does in a place like Minnesota or North Dakota. And there's factors other than just the ocean itself. There are actually some warm water currents, like the Gulf Stream, that bring warm water to New York and nearby areas. And that's part of why the Atlantic Ocean doesn't feel as cold as the Pacific Ocean. But still, the coldest parts of the continental US are usually quite far from the lakes and also, quite far from the ocean and also farther from the Great Lakes. I love Minnesota, but it is deathly cold. And then if you go into the Dakotas, it gets even colder. You'll notice that even by the Great Lakes, it's a little milder than it is here because the Great Lakes don't have as much water and don't serve as quite as strong a regulating presence. but their presence still helps. The farther you get away from the lakes, the colder it gets. And that is very simplified. This is also just one particular weather snapshot, but you will see a lot of maps like this if you look at what the average temperatures in the US are on a given day. And on a smaller scale, you'll notice that if you are someone from California and you've spent a lot of time in California, you'll realize the coasts feel nice. It doesn't get too hot, get too cold. Then you go into the Central Valley, and in the summer it's 100 degrees there and it's cold at night. You go out into the desert and it's above 100 degrees in the day in the summer, and then the temperature drops to frigid at night. And that's because you're further from the ocean. The rock and the other solid substances surrounding you do not regulate the temperature as well as the ocean does. I talked about latitude before. Latitude is whether you are north or south from the equator, and we'll talk more about the details of that in this lecture also. But the Earth is tilted on an axis. The Earth is not facing the sun head on. And because of this tilt, the equator gets strong sunlight pretty much all year round. The sunlight is hitting the equator at a direct angle. Now, if you look at the diagram on the left, you'll see that the angles get progressively smaller as you approach either the North or South Pole. And that's because the sunlight is hitting the Earth more at an angle because the Earth is kind of tilted and curved away from it. The sunlight is literally being spread across a greater surface. Sunlight, even though sunlight is to some extent a finite quantity, there's a certain amount of solar radiation coming from the sun to the Earth. And if that's concentrated, if it's hitting the Earth directly, then it's going to feel warm. If that's spread out, if it's hitting the Earth kind of at an angle and being spread over a larger surface area, it's going to feel like a weak sun. The polar sun feels like a different star almost, and the light looks different. When I was in Antarctica, the sunlight was bright, but it was kind of filtered. It felt like everything was filtered. I also had to be careful of the UV radiation. But this contributes a lot to Earth's overall climate and circulation. The solar radiation is not evenly distributed across the Earth. This is why the Arctic and the Antarctic, this is one reason why both the Arctic and the Antarctic are so cold. Not at the same time of year, of course. In this diagram, you can see that the people in Alaska and Siberia are getting the midnight sun, but people in Antarctica, those poor people who might be wintering over there, are going to experience quite a bit of complete darkness. And this also contributes to average temperatures being so low, because even if you have a reasonably balmy summer, you're going to have a winter at both the North and South Pole that's going to be in complete darkness and thus much colder than winter in California or winter in Argentina or winter in Australia for that reason. Returning to the circumpolar current. This is something that is particular to Antarctica and not really found in the Arctic, because remember there's no continent on the North Pole. There's an ice sheet and you can walk on that. There's ice and you can walk on that, but there's no continent of Arctica. And Antarctica as a continent has been isolated from the other continents for quite a while, speaking in terms of geologic time. We will learn more about that later. What this means, however, is that a current has developed around the entire continent, moving water rapidly and being essentially uninterrupted. There is a vortex of seawater moving clockwise around Antarctica. It is cold water, and it's very hard for any warm water from more temperate latitudes to mix with that. In this diagram, you kind of just see that any warmer water, in the diagram below, you just see that any warmer water kind of just gets blocked out. And this is the only continent that has a current running all the way around it. It's the only current in the world that makes a complete loop. And it is moving fast. What scientists use to measure the movement of the Antarctic Circumpolar Current is a unit called a sverdrup, which is it is 1 million meters cubed of whatever substance you're interested in this case seawater, per second. So it's a rate. It's the volume of water moved every second. And it ranges from 100 to 150 sverdrups, which is higher than any other current in the world. It is essentially the largest current in the world in that regard, even though it doesn't allow a lot of water to reach Antarctica, because the Southern Ocean connects the Pacific, the Atlantic, and the Indian Oceans. It allows for a decent amount of mixing of water as well as nutrients, and in some cases wildlife between the three. So it has played a large role in the the story of the oceans ever since it developed, not just in terms of making Antarctica cold and isolated, but also in terms of mixing ocean currents. Now, I mentioned that a lot of people don't realize how dry Antarctica is. And Antarctica gets less than 2 inches of rain a year on average. Most of the continent, with the exception of a few areas near the Antarctic Peninsula in the diagram on the right, the darker areas like those in the northern Antarctic Peninsula get a little more snowfall. Now, Antarctica is a desert. When I was there, it felt like I was being in Utah or Arizona. You can just feel the dry air evaporating all the water out of your body, and it's really unpleasant, frankly. And when the wind is blowing, it is even worse. And the ice in Antarctica doesn't get there because it snows a lot. It is so cold that it basically never drops below freezing and goes above freezing, excuse me. And so the ice accumulates very slowly and almost undisturbed for hundreds, thousands, and even millions of years. So Antarctica is a desert with glaciers. It is, in fact, inside of what you would consider one of the desert belts. Something we'll talk about during the climate unit is how certain latitudes of Earth, areas north or south of the equator, are likely or unlikely to get lots of rain based on the air pressure. Antarctica is in a high pressure zone. High pressure means you have a lot of dry air falling, in this case actually at the center of the continent. In addition to meaning that Antarctica doesn't have much rain, this also contributes to Antarctica being so windy. The air settles down at the center of Antarctica and then makes its way towards the coasts over the ice sheet. The other thing to consider is that, remember the continental effect. Antarctica is very far from the ocean for the most part. Yes, you have a coast, but most of Antarctica is very far from it. And the interiors of continents are often vast deserts because of the temperature fluctuations and because the ocean often is what brings moisture. It's winds from the ocean that bring moisture to places like California. And California, that moisture reaches as far as the Sierra Nevada. And then when you get to the state of Nevada, it's the Great Basin Desert. Beautiful desert, but very much a desert. Most moisture that does reach Antarctica, you get it on the edges, then you go to the interior and it's dry as a bone. And there's really just not much in the way of wet years in Antarctica. If you look at this precipitation map of Santa Barbara, you can see that even though we've sometimes had years where we got 7 inches of rain or 6, not that far off from 2 inches, there have been other years where we had 45 inches of rain in the entire year, or 47, or on average something like 17. You'll notice if you look closely, the red line is here to demarcate the average rainfall in Santa Barbara. And as you can see, the average is somewhere near 17, a lot bigger than 5. So we kind of live in a desert, but nothing compared to Antarctica. And the wind has to do a lot with the air masses falling at the center of the continent. Antarctica is largely considered to be the windiest continent, both because of average wind speeds and because the winds are just a near constant presence. The winds in Antarctica are often known as pressure winds because remember that there is a high pressure zone at the South Pole. Air is falling there. Antarctica is higher in the interior. The ice sheet is built up more in the interior. And what this means is that the air traveling out from the center of Antarctica kind of gets accelerated by the slope. And you get this drainage wind, this wind that is taking air downslope due to gravity from the center of the continent to the edge. These can be very intense, and they can be further intensified if these air currents flow into a valley, which will make a wind tunnel. In the dry valleys where I was, in fact, the dry valleys were kept ice-free because these already strong winds were strengthened even more by them dipping into these valleys. And the Southern Ocean is also considered to be the world's stormiest ocean. Wind can blow uninterrupted around the continent, and the Southern Ocean has been a very dangerous place for anybody to go. Most people who went anywhere near the Southern Ocean decided, this is dangerous, I don't want to die. Obviously, some people did decide to venture in, and many people did perish because Antarctica has always been a dangerous place. Someone needed to make that venture into the Southern Ocean to realize that a continent exists there, but it's it is generally safer actually to fly to Antarctica than to take a ship. Even with larger vessels, the larger vessels can usually handle the storms just fine, but it is usually safer to fly. Now, something you might be wondering about is why I describe Antarctica as the highest continent, because people know that Mount Everest is the highest point on Earth. Well, I've mentioned average versus individual measuring sometimes, and the Antarctic continent has the highest average elevation, which is if you take a computer model and get an approximation of all of the different elevations and then use computer modeling to figure out what that average is about to, you end up with a much higher elevation than any other continent because there aren't really any lowlands that you would get in Asia. Asia has the world's highest point, Mount Everest, but Asia also has the Bengal Delta and the Dead Sea, coastal areas of China, low-lying islands that cancel that out significantly. Asia is still a high continent, but it's much more varied than Antarctica, and that lowers the average elevation. If you look at this map of Antarctica, it's kind of smooth looking. It looks like you're looking at this ice dome. And you can see mountains sticking out in a few places, but the ice sheets are covering the mountains. The East Antarctic ice sheet, which is what you're looking at here, is covering the mountains and valleys and kind of averaging everything out. You don't really have a lot of valleys visible here. And what that means is that the average height is really high. And what this brings me into is that Antarctica is topographically quite an interesting place because you have mountains and valleys, but you are also dealing with the fact that you have this ice sheet covering all of them. And what is topography? Topography is the study of landforms like mountains, valleys, plains, oceans, canyons, and specifically using a tool to map the elevations of those features and put them on a map. Why is that important? Because we need topographic maps to do research in Antarctica, for one thing, to know what kind of terrain we're dealing with. And in a more close to home setting, urban planners will use that to figure out if an area is safe to build on, or if they're even trying to build a city, if this area has terrain that is appropriate for a city. And now we will find that Antarctica looks quite different from this if you actually get any image of what it looks like under the ice. And topographically, it is much more varied, but the average heights are being considered based on the glaciers. Talking about topography, a topographic map is a type of map that uses contour lines to show which points on the map are the same elevation. It exists to help one visualize mountains or valleys on a two-dimensional surface. And they take quite a bit of practice to look at and interpret confidently. However, I used to struggle with these and I've gotten better at them. A lot of it just relates to practice visualizing. So this is one good example of how topographic maps convert 3D information into 2D information. So on a topographic map like this, each line is kind of a fancy connect the dots exercise. It is all of the points that have the same height, the same elevation, whether that's, in this example, the highest contour line given is 1,400 feet. And if you squint closely, you'll notice that there is a line labeled with 1,400 feet. There is a line labeled with 1,400 feet inside of here. You'll notice that there is one labeled 1,100 feet on the outside. You have lower points on the outside making a line, and then progressively higher lines on the inside. And this is how you can show a mountain on a two-dimensional surface without simply drawing in mountains like you would find on like a Lord of the Rings map. I love those, but scientists don't really love those because it's hard to, what you need a topographic map for is you need to accurately and systematically be able to convert every point on at least every point, most of the points on a 3D image to a 2D image. They need to relate to one another. There has to be a system for how one mountain is converted into topographic lines. So each contour line represents a different elevation. Any point, if I trace this line, every point is the same elevation. Contour lines will never cross for that reason. You will never see contour lines cross. The numbers refer to how high they are. And you'll notice that the lines in this diagram are the same distance. 1100 to 1200 is 100, 1200 to 300 is also 100, and 1300 to 1400 is also 100. There is a difference of 100 feet between the lines, and that is the contour interval. It will always be the same for a particular map. And that's what that does is that it helps us illustrate just how much horizontal ground one has to go over to climb a certain distance vertically, like to climb a mountain. If the contour lines are on a map kind of spread out, like a little more at the edge of this mountain, like at the foothills, then that means that it's kind of a gentle slope. You have to cover quite a bit of horizontal distance to go up the amount of vertical distance, the amount of elevation specified by the contour interval. However, when they are really close together, like this in the middle, that means that you are climbing. You are going just a little bit of horizontal distance and going up, up, up. And it might be a little bit hard to see in this broadcast, but likewise, you can see that the lines are spread apart near Lake Vanda, which is on a plain, and they get closer and closer together on either side of it. These are the mountains on either side of the Wright Valley, which is where I was based. And this is how we found our way around Antarctica. The topographic maps, we would put our geology notes on top of this, and it would help us decide, okay, how far do we have to hike, and what kind of terrain do we have to hike over? Maps are useful because they show distances. Topographic maps are often put over geographic maps or geologic maps to show you what kind of terrain you're going to walk over. You want to know if you want to know how far you have to go. Like you want to know, okay, do I have to walk 250 miles or not that much, 25 miles? If you know you have to walk 25 miles, it is very helpful to know if you are going to be climbing over mountains or if you're just going to be walking in a floodplain or something like that. Topographic maps are not the only type of maps we deal with, though. People usually think of a map as, okay, this shows where countries and continents are. And in Antarctica, there's no countries, obviously, but we use maps to show features and get around. Now, maps are difficult in that they are an artificial construction. You are turning a 3D globe into a 2D image. And this means that the image gets distorted, especially near the poles. A map projection is a model used to systematically convert geographic points on a 3D globe onto a 2D map. And these projections are traditionally centered at the equator, which is reasonable, but what that tends to do is make the areas near the poles look really weird. Like in all these maps you see where Greenland is like 4 times the size of India, even though Greenland is actually slightly larger than the country of India. And Greenland is close to the North Pole, so that's why it gets so distorted. And that's one reason I really don't like this projection, which is known as the Mercator projection. It's one that you see a lot in grade school textbooks, and it's reasonably useful, but the distortion drives me crazy. No map is going to be completely free of distortion, but for a class like Antarctica, using the Mercator projection is generally not very helpful if you're trying to accurately measure distances. And it turns out a lot of this has to do with the fact that the lines of longitude, the lines that tell you distance east to west, they converge at the North and South poles. And when you try to spread those out on a map, it really badly messes up the way the continents near the poles actually look. Another concept I want to introduce is the concept of hemispheres. Hemispheres are a method that us humans use to somewhat arbitrarily demarcate different areas of the world. And it's kind of a theoretical construction. Half of a planet, hemisphere means half of a sphere. And the equator is the reference line. And if we're going to talk about the northern versus the southern hemisphere, the equator is the reference line. Everything north of it is the northern hemisphere, and everything south of it is the southern hemisphere, which includes Antarctica. You may also hear about the western and eastern hemisphere. And consider that as a separate concept. Just as there is a line dividing the northern half of the globe from the southern half of the globe, there is another line, a bit more of an arbitrary one, dividing the western half of the globe from the eastern half of the globe, the western and eastern hemispheres. There is no west or east pole, so there was no, and there's no, so there's no obvious. This is the line we need to pick in between them, the same way that the equator lies between the north and south poles. Hypothetically, you could pick any north to south line as the reference point. Because so much of this science was initially done in Europe, European scientists chose the line of latitude that goes through London, or Greenwich as it was known in the past. And that is why what is known as the prime meridian now, 0 degrees when we're talking about distance east or west, runs through London. It runs through London and actually runs north to the North Pole and south to the South Pole. You'll notice that all of these lines that are going up and down, the lines of longitude, converge at the poles. It's a little bit easier to see in some other diagrams. The lines of latitude, the ones that go side to side, they don't converge anywhere. You'll also notice that they're all spaced the same distance apart. You will want to remember that Antarctica is in the southern hemisphere. Should be a pretty obvious point, but that does affect things like the Coriolis effect and seasons. So keep that as a reference point. Now let's talk a little bit about longitude and latitude, or excuse me, I usually put latitude first. Latitude and longitude are a coordinate system. They are based on numbers, and they are based on lines in which each line represents points that have the same distance north or south from the equator, or the line consists of points that are all the exact same distance east or west from the prime meridian. Lines of latitude, they extend horizontally, so they run east to west, but they all demarcate distance north or south relative to the equator. The equator is a line of latitude that is 0. It is 0 distance from the equator. 30 degrees, you have this line that is 30 degrees north. It is all the points running east to west that are 30 degrees north of the equator. Likewise, you have 30 degrees south, which is all of the points that lie 30 degrees south of the equator. And degrees are a unit of distance measurement fundamentally in this case. That's what we are talking about. The north and south poles are 90 degrees north and 90 degrees south, respectively. Now, moving on to lines of longitude, you'll notice that they don't really quite have the same geometry. Instead of these evenly spaced out lines, they all get closer together at the poles and they all converge at the poles. You'll also notice that there really isn't an east or west pole, just like I mentioned. We have the prime meridian, which we kind of somewhat arbitrarily set as the dividing line, and that actually runs through the North Pole and onto the other side. On the other side, we consider that to be 180 degrees. 180 degrees is approximately corresponds to what has since been defined as the international date line, which is how time zones and day are defined. Because remember, the Earth is rotating this way. It's not rotating up and down. That would be surreal and probably horrifying if the poles were doing that. But anyway, you need both to pinpoint a location. If you simply have a line of latitude, I'm 30 degrees, I could be like, well, are you in Florida? Are you in Mexico? Are you in Europe? What do you mean by 30 degrees? Like, where are 30 degrees? So what you'll do is you'll give a latitude and a longitude. Latitude comes first. In this particular case, these are the coordinates for Goleta, California. There is actually more than one way to subdivide a degree for latitude and longitude. This measurement here simply gives them as decimal points. However, you can also divide them into what are called minutes and seconds. Each degree of latitude or longitude can be divided into 60 minutes, and each minute can be divided into 60 seconds. It'll be written with the minutes as a little apostrophe and the seconds as a little quotation mark. And you just need to know what you're working with. The map or the assignment, if you are doing this for an assignment, the assignment will establish what you are working with. This is one case where, yes, the word similarity actually helps a lot. Just as you have 60 minutes in an hour, you have 60 minutes in a degree. Just as you have 60 seconds in a minute, When we're talking about time, you have 60 seconds and a minute when we're talking about longitude and latitude. And this is another way to kind of indicate just the lines. The lines don't really quite have the same geometry. The lines of latitude form what are called small circles, and that they don't actually, at least not all of them, intersect the center of the sphere. But every line of longitude is a great circle that passes through the center of the sphere, which is why you end up with every line of longitude ultimately converging north at the poles. And when you're at the South Pole, it's kind of hard to say how east or west you are, because you could pick a direction and walk to and follow any line of longitude to anywhere, hypothetically. Obviously, nobody can do that because you're in Antarctica. But I understand that latitude and longitude can be a little bit of an intimidating subject. There is a mnemonic on the previous slide, and the TAs and I are very happy to help you out with any concerns or issues. Please contact us during our office hours, and we will very happily go over this with you. Especially, I highly recommend checking with me or with the TAs if when you see the lab materials next week, you end up finding that challenging. So the fact that the lines of longitudes converge at the poles means that we had to think of another system. We had to develop a polar projection that is based on the South Pole, or the North Pole if you're studying the Arctic, as the center. And this means that the distortion is going to be more noticeable away from the pole, but we don't really necessarily have that much of an interest in mapping at Africa or South America when we're talking about Antarctica. You will often see that a world map that has a equatorial projection will have a little inset with a map of Antarctica that looks like this to show you more accurately what the continent looks like. When I was writing my thesis, I had to play around with different polar projections because there is not just one, unfortunately. But I had to play around with different ones to get it to work perfectly with the GPS data I had. And that was quite time consuming. Now, another question, how big is Antarctica? It's the 5th largest continent. If you don't count Europe and Asia separately, it is the 5th largest continent. It's larger than Europe, and it is larger than Australia. It is also larger than the entire US, and that is indeed if you include Alaska. It is not bigger than the North American continent, but it's bigger than many large countries. It's bigger than North America, bigger than the United States, bigger than India. And these are big country-sized areas that are just covered in ice and snow. Over 99% of all of this is just a wasteland of ice and snow. A very beautiful wasteland, but fundamentally that. There is just so much ice present on the continent. At a given time, there are tens of millions of kilometers squared of ice present on the entire continent. This is a gigantic pair of ice sheets. There are 2 separate ice sheets, in fact, the West Antarctic and the East Antarctic. They have both been present to some extent for about 25 million years. However, that is about when they assumed their current conditions, and they had probably been there just in smaller form even earlier, possibly as early as 40 million years ago, about 20 million years after most dinosaurs died, essentially. And by the way, MA means mega-annum, or millions of years, so that's an abbreviation that you will see again, definitely when we do paleontology. Now, Antarctica is really different if you take the glaciers away. This map on the left shows you what would look like if the glaciers weren't there, like if they melted. And this is the topography beneath the glaciers. And you'll notice that there is quite a bit of blue, the negative numbers. If you have a topographic map and you have negative numbers, that's not an error. 0 on a topographic map is sea level. Positive numbers mean higher and higher mountains, so Mount Everest is going to have a lot of closely together spaced contour lines with high numbers. Antarctica, if you actually look at its topography below the glaciers, a lot of it has sunk down a lot. That is simply because the glacier is so big that it is pushing the continent below sea level. It is pushing the rock underneath it, actually physically into the Earth's mantle. That is something called isostasy that we will return to. Now, if all the ice were to melt, God forbid, because that would be a mess for this country, a mess for the world, but it would actually slowly rebound over time. With the ice gone, that pressure that was pushing it down would be gone, and it would eventually start to behave a little more like a regular continent and not be sunken under the sea. But that would take millions of years. Oops. I do apologize for moments like that. I'm still getting used to this format. If we look underneath the ice, we have to do it with satellites. We use satellites actually the references have gotten better. A recent this is a comparison between a newer satellite map of the subglacial parts of Antarctica versus an older one. And the resolution has gotten better because we have more satellites, we have more advanced satellites that can take measurements over a longer period of time. We can have supercomputers that can compile the data and put them into a recognizable image. We can't really go under there, though. Our understanding of the ice is getting better with satellite technology and with supercomputers and with improved technology in general, but we can't really go under here. We can just try to look at what's under there and hope that our guess is reasonably accurate. Briefly, I want to talk about the regions of Antarctica. We are approaching, I realize that this first lecture is a bit longer. The second half of lecture 2 will be quite short compared to this. This will be one of the few examples where this goes on for longer. Antarctica is divided into East and West Antarctica by the Transantarctic Mountains. It's a naming convention, but West Antarctica is the smaller bulb with the peninsula, and then East Antarctica is this much bigger mass. The South Pole actually isn't that far from the coast, all things considered, and it's pretty darn close to the boundary between East and West Antarctica. East Antarctica is a lot larger. It's also where I was. My research area was down here in the Ross Sea. And East Antarctica is one giant mass of rock. It has actually been more or less all stable together since very early on in Earth's history. It's very geologically stable, and we'll talk more about what that means in the geology unit. But now let's introduce some of the important geographic points. We know where the South Pole is, but what South Pole do I mean? Oops. Well, when I talk about the South Pole, I'm referring specifically to the South Geographic Pole, the southernmost point on Earth. There is also something called the South Magnetic Pole. Earth is a magnet. Earth is essentially one giant weak magnet, and even though it's a weak magnet, the magnetic field, which is produced by molten iron in Earth's core, does serve to keep solar wind from killing all of us, and it also contributes to the existence of the aurora australis, the southern lights. It moves. The magnetic poles do not stay in the same place. Also, periodically, the north and south magnetic poles flip, and we'll talk about that also. But on this diagram, this is where the magnetic pole was in 2008. It had wandered quite a bit since it was mapped in 1914. So the magnetic pole changes location significantly during people's lifetimes, and that's why geologic maps that have anything to do with magnetism have to make a note of when they were made so that they can indicate what measurements they were taking relative to what geographic pole. There is also something called the pole of inaccessibility, which is the farthest point from any ocean. And it turns out that is not the geographic South Pole. The geographic South Pole is actually relatively close to the ocean. Now, what is an ice sheet? I mentioned ice sheets a couple times, but ice sheets are enormous glaciers. There is essentially one enormous glacier covering all of East Antarctica, and then a smaller one covering most of West Antarctica. You have a massive ice moving out to the ocean, and when it moves out to the ocean, you get an ice shelf. Ice shelves are actually the extensions of glaciers that go over the ocean. And these ice shelves are, to a big extent, these ice sheets, are what is used to define East versus West Antarctica. They are two separate and differently behaving ice sheets. East Antarctic ice sheet is much thicker, it is much steeper. It also importantly kind of flows out in all directions. You have ice accumulating at the center and flowing almost like a stream. And when we learn more about glaciers, I will talk about how glaciers fundamentally are frozen streams. And West Antarctica, which is a much smaller area, actually has more of a single stream in which smaller ice flows flow into. Because it is so much more close to the ocean, it's less stable. Its temperature fluctuates more and it has had less time to build up. It is presently much more at risk of damage from global warming because of this, because the ocean is warming rapidly and the West Antarctic ice sheet is going to be much more affected by warming ocean water. And this is another cross-section to give you a general idea. You'll see that if you actually try to run from one side of the Antarctic to the other, the West Antarctic ice sheet is kind of tiny compared to the East Antarctic ice sheet. Not trivial by any stretch, but relatively tiny, all things considered. There are not a lot of places in Antarctica that don't have ice. You are either going to be close to the coast, where the continental effect and the effect of the ocean makes it a little balmier. You might have volcanoes like this. I wish I got a better picture of Mount Erebus, but this is the picture I got to take of Mount Erebus. And volcanoes produce heat, which keeps them relatively ice-free. You're also going to have some mountains sticking out. You'll also have these little things that are called nunataks. Those aren't quite mountains. They're not nearly as tall as Mount Erebus, but they're little hills, basically, that stick out of the glacier. And then you have the dry valleys, which are kept free by the winds. And we will come back to the dry valleys, but what causes them is essentially a wind tunnel. A wind tunnel combined with high enough mountains that the glaciers don't flow into them and that any ice that builds up in them is just blown away. So you end up with this very heavily protected, very desolate, very sparse, very, very beautiful and very rocky area called the dry valleys. These are indeed dry. These actually get less precipitation than Antarctica does in a given year. They are virtually lifeless at the macroscopic scale. Remember the seal mummies from lecture 1? They had nothing to eat there. However, there are some very interesting microorganisms at work there. Antarctica physically is surrounded by the Southern Ocean, and there are also several seas, these smaller bodies of water that are sort of hemmed in by land, like the Ross Sea, near where I was working, and the Weddell Sea. And something I want to bring up that we'll come back to later is that there is a difference between sea ice and ice shelves. Ice shelves, as I mentioned before, are the extensions of glaciers that go out over the water. Sea ice is the ice that just forms on the surface of the water itself, kind of like pond scum. It freezes in the winter. Much of it goes away in the summer. The ice shelves do not disappear in the summer. The ice shelves shown here are considered to be permanent ice. However, they are beginning to break up from global warming. What this means is that you are going to be dealing with ice year-round going to Antarctica. You have to have these icebreaker ships that have strengthened hulls and the horsepower to plow through the ice, and they have to go in the summer. This is one reason why getting off Antarctica in the winter is nearly impossible, because not only do you have an ice shelf that is strengthened by the cold, you also have sea ice everywhere, and you kind of have to wait until the summer for some of that to melt away. One of the weirder features about Antarctica is that there are lakes under the glaciers. There are lakes caused by geothermal heat, as well as the fact that if you increase the pressure, water can exist as a liquid below 0 degrees Celsius. And one thing you'll notice in this diagram is that there's rivers. There's lakes mapped, and there've also been rivers connecting these lakes, just as you would have rivers connecting a watershed in California or in anywhere else. We can't really go here. We know that they exist because of satellite images and other indirect methods. They are essentially alien landscapes to us. We don't really know what lives there. They're obviously going to be organisms from Earth, but there is a lot of concern about exploring these lakes and possibly killing any microbiotic life that lives there, or introducing species. And it's also just hard to get below the massive layer of ice. So they are largely just a mysterious zone that we can't really look at much yet, and we don't know a lot about what's going on in the subglacial lakes. That is actually one of the bigger fields of research right now. I'll talk more about the geology of the Transantarctic Mountains during another slide, but they are the main mountain range that you will want to know. They actually run all the way from Victoria Land to the peninsula. The peninsula is actually kind of an extension of the Transantarctic Mountains, and they separate the much smaller West Antarctica from the much larger East Antarctica. And they are the most prominent mountains that stick out. You'll see that there's a decent amount of ice-free areas in the Transantarctic Mountains, and they are actually right by where the dry valleys are. There are other mountains out here, but they are largely covered up. The Antarctic Peninsula, the northernmost extension of the Transantarctic Mountains, is by far the warmest part of the continent. It is surrounded by ocean and farther north, and those two factors mean that it has more varied temperatures. It also means that you have warm enough climates and enough soil formation to have a couple of flowering plants in addition to lichens and mosses. I didn't see any plants outside of a couple of lichens and one moss the entire time I was in the dry valleys. The peninsula is by and large a paradise compared to where I was, just in terms of plant life. And what's happening right now in the peninsula is because it is the fastest warming part of the continent. It is the warmest to begin with, and it is warming extremely rapidly due to global warming because so much of it is surrounded by the ocean, and the ocean temperatures are rising. One of the results of this is that these two plants, the Antarctic pearlwort and Antarctic hairgrass, are expanding. They're expanding to areas of the continent that they were not found in before because it is now warm enough for them to exist there. The Antarctic Circle is a line that is used to define every area that will experience at least one day of 24-hour darkness and at least one day of 24-hour sunlight. This has actually varied over geologic time because Earth's tilt has varied over geologic time, meaning that where exactly in the Earth is going to have complete darkness wasn't necessarily the same as during the dinosaur age as it is now. And not all of Antarctica is actually south of the Antarctic Circle. A little bit of the peninsula and some stuff in the east is actually north of it. And this is one reason why the Antarctic Circle isn't always what people use to define what is Antarctica. Another important meter is the Antarctic Convergence. And the convergence is a front. In climate and weather terms, a front is where two moving masses of either water or air meet. And what happens at the Antarctic Convergence is that you have cold water flowing northward from Antarctica, meeting warmer subantarctic waters. The water flowing from the south sinks below. This actually ends up producing a lot of upwelling, and it allows for a bloom of wildlife in the summer. However, this actually is noticeable as a temperature difference. From the north of the Antarctic Convergence going south, you will see a drop from 6 degrees Celsius to 2 degrees Celsius, or 43 degrees Fahrenheit to 35 degrees Fahrenheit. You could hypothetically, you would not want to be swimming in that water, but you can feel that difference. You can feel the second you go south of the convergence. And presently, the entire continent of Antarctica is south of the convergence, as are many other islands, which we will talk about in the next slide briefly. But this does not really exist in the Arctic. Nothing equivalent exists in the Arctic because it is surrounded by land. The islands that you saw in that last diagram are the Subantarctic Islands, smaller land masses south of the convergence where many of the animals that we think of as Antarctic animals, like a lot of species of penguins, actually breed, because since these islands have a much smaller landmass and are surrounded by ocean, they tend to be a little bit milder than the interior of Antarctica. So a lot of penguins breed there. They have high seal and whale populations. That is also why islands like South Georgia Island, which we'll talk about later, was used as a whaling base, and why Shackleton would seek refuge there because he was trying to meet up with the whalers. Whew, that's a lot of physical geography. Don't worry, the second half of the second lecture will be a bit shorter and just about the relatively small human presence. Please ask me questions and shoot me emails about this because this is a lot and the latitude longitude thing can be confusing, but I will see you for lecture 2B when you open up that video.